Let's start. So, very good evening to everyone. This is live discussion session for NPTEL course Basic Thermodynamics, Classical and Statistical Approaches. And this course has course code NOC24CY04. And myself, Akash Gutal, I'm PhD student from Indian Institute of Technology, Jodhpur, Department of Chemistry. So, let's first revise last week's lectures and uh, some formulas that we have seen in that lectures. So, we started uh, different conditions for spontaneity. So, different conditions for spontaneity we have seen. So, we know that for spontaneous process, entropy is always increasing, but only entropy is not only condition for uh, determination of whether the a given process is spontaneous or not. So we know that entropy is not alone sufficient to determine spontaneity. So we have seen uh, how uh, we can evaluate certain the conditions regarding which can uh, tell us that given process is spontaneous or not. So from that we have seen four such conditions. The first one, as we know, it's related to uh, your, of course, entropy. We have, sorry. So for entropy, at the change in entropy at constant internal energy and volume should be greater than or equal to zero. So this is the first condition. And second condition that we had seen is change in internal energy at constant volume and entropy. This must be less than zero. The third condition is about change in Helmholtz free energy at constant volume and temperature must be less than zero. And the fourth that we well known is change in Gibbs free energy, constant pressure and temperature must be less than zero. So these are four conditions for determining the process is spontaneous. And most of the times we use Gibbs free energy as our measure to check whether the process is spontaneous or not. We have seen this gives use of Gibbs free energy for determining the spontaneity of the process in biological application, the drug and uh, The complex between the drug and protein uh, is well-known example that where we check the binding of drug to the particular protein, and we check its free energy, gives free energy, whether the process is spontaneous or not. So if the change in Gibbs free energy is negative, then we call the process is spontaneous. So it's also true for other three conditions also. But mostly we use delta G, that is change in Gibbs free energy. Then we have seen the Legendre's transform. Legendre transforms. From there, we have seen how we can evaluate del U. U is equal to TdS minus PdV. And we know the del H is nothing but TdS plus VdP. Similarly, del A, that's change in Helmholtz energy, is minus SdT minus PdV, and from dG, the change in Gibbs free energy is minus S dt plus VdP. So, so these are important um, differential expressions. And after that, we have seen uh, the Maxwell's relations. So, in case of Maxwell's relation, so to remember the Maxwell's relation, we have mnemonics, uh, which can be given as, let's say, S P T and P. So we this mnemonic we have seen in class also, and we know this is for sign convention, and we know S the U internal energy is function of S and, oh sorry, internal energy is function of S and P, and enthalpy H is function of S and P. Then we have uh, Gibbs free energy G is function of P and T, and has Helmholtz free energy is A is function of V and T. From this mnemonics, we can write all four Maxwell's relations. So, so there is one simple method than mnemonics also there. I will tell you. First, we will write left hand side using this mnemonics. Let's say we'll start with del T by T and V, relation between del T by del V. So this is our left hand side of Maxwell's relation. And when we are writing right hand side, so what we need to follow is the denominator of left hand side and the numerator of right hand side, if multiplied, must get the dimension of energy. Okay, and by using just left hand side, you can write right hand side by using the same rule. how we can write here in left hand side, denominator is volume, the dimension is volume, and what should be the numerator dimension here? What can be multiplied to the volume, which can give you uh, energy as a dimension, which is nothing but the pressure. PV is actually having energy of the dimension of energy. And similarly, ST is also having dimension of energy. So what using this small principle, we can write the numerator of right hand side must be del P, and the denominator of the right hand side must be T and be S. And the constants uh, are for the left hand side, the constant would be the dimension or the quantity, and the right hand side's denominator is S. And similarly for the right hand side, the left hand side's denominator V. And then we need to determine its sign. It's also important that we need to determine its sign. How to remember sign? We don't need to remember sign. Just need to understand how sign works. We know that temperature and volume are directly proportional. If you see temperature and volume, we know PV is equal to nRT. V and T are directly proportional, and we don't know what pressure and entropy. So we need to check that. So whatever the proportionality of left hand side, if it is not present at the right hand side, here T and V are directly proportional, and here P and S are, if we increase the pressure, entropy must decrease. So that are inversely proportional. So if such condition happens, then we need to include negative sign here. Okay, let me write this negative sign here. Why? Because as T and V are directly proportional, change in volume, positive change in volume will bring positive change in temperature, which make this left hand side as a positive. But in case of right hand side, positive change in pressure will cause negative change in uh, entropy, which is actually gives you the negative number. To make that negative number positive, because our left hand side is having a positive attribute, we need to introduce this negative sign. So uh, that is the reason why this negative sign appears naturally in this equation. So you need to check only the relation, or we can say the inverse or direct relation of these numerator and denominator at the both side of the equation, left and right side, right hand side. If they are both are having directly proportional, then your sign will be positive. If one has left hand side has directly proportionality and right hand side has inverse proportionality, then your sign will be negative, will be there in the equation, Maxwell's relation. Similarly, we can write, let's write for equation about del S by del V. So what will be the right hand side? What is the counterpart of del V is del P. To get the energy dimension for S is del T. And the constants are, this will be V and this will be T. Similarly, we will check whether our uh, proportionality, pressure and temperature are directly proportional. S and V, entropy and volume. When you increase the volume, entropy will increase. When we decrease the volume, entropy will decrease. So both are directly proportional, so no negative sign. If you if you do it for change in S and P, Can write right hand side as del V by del T. Constant of the constants are P and T. Similarly, we will check. So V and T are directly proportional, and S and P again they are inversely proportional. So here we must include a negative sign. Similarly, we can write the last equation del T by del P is counterpart del V by del S at constant pressure and entropy. You can check here also. T and P are directly proportional. S and V are actually directly proportional. So we don't need to include negative sign. So these are the four Maxwell's relation. Now we can solve. You can solve any problem from the which arises from the Maxwell's relation. If you know left hand side, you definitely don't know the right hand side with the sign. Sign is important. The next thing that we have seen last week is some formulas related to coefficient of coefficients. So first is coefficient of thermal expansion. We denoted alpha is 1 upon V dV by dt, constant pressure. And we know the kappa, that is coefficient of isothermal expansion, is minus 1 by V del V by del P, constant. Here also the sign can be remembered uh, using proportionality. T and V are directly proportional. So the sign is positive in case of alpha, and in case of kappa, K, you can see V and P are inversely proportional because PV is equal to nRT. If you keep in right hand side, then it will be 1 by V. So P and V are inversely proportional. Due to this inverse proportionality, this del V by del P will come out to be negative number. But we need to define a coefficient of coefficient by thermal expansion. Then to make it positive, we need to include the negative sign in the equation. That will naturally uh, brings entire term as positive. And we have defined the heat capacities. Cp in terms of entropy and temperature. Cv as T delta S by delta T. And we should not forget that any thermodynamic derivatives can be expressed in the form of the above heat capacities. So why we define this is, so any derivative form that we have seen before can be expressed in the combination of alpha, kappa T, and Cp and Cv. And And we know that these quantities are measurable. We can do the experiments and we can measure them with using the experiments. And because they are measurable, we can express the quantities which we can't measure in terms of these experimentally measurable quantities, so that we can understand uh, the non-measurable or the complex thermodynamics derivatives. And also we have seen this thing uh, in our last lecture also, how we can express this thermodynamic derivatives in terms of Cp, Cv, alpha and kappa T. So and this gives us a very good tool to actually determine these thermodynamic values of these thermodynamic derivatives. And another important relation that we have seen is Cp is equal to, sorry, we can write here directly. Cp is equal to minus T del 2G by del E square at constant function. This is an important relation we need to remember. So this completes with the revision. Let's solve some problems related to the same. So the question number one is, which of the following is not a condition for spontaneity of a process? We have seen this question, or the discussion related to the question. So here we need to determine which is not the condition for the spontaneity. So we know that change in entropy is actually greater than or equal to del Q by T, del Q by T, temperature T. And we know that T ds is, so this ds entropy, change in entropy becomes equal to del Q by del T for only reversible process. Other process, it will be greater than del Q by T. So TdS is greater than or equal to del dq. So if we take dq at the left hand side, it will give us rho TdS minus dq is greater than or equal to 0. If you replace, we know dq is equal to u uh, plus pdv. And similarly, we can write this TdS minus u minus pdv is greater than or equal to 0. And this is a minus u, and if we change the sign of the inequality, then we should change the inequality as u plus pdv minus tds, where the spontaneity, the condition for spontaneity we can get from this equation is u, or we can say the du. Sorry for that, it should be du. Okay. Du must be less than 0. This will be condition for spontaneity. Similarly, you can show ds. Okay, this condition only valid at constant entropy and volume. Similarly, we can show it for del S for a constant volume and internal energy. It should be greater than 0. Similarly, for Gibbs-Helmholtz energy, del A uh, constant volume and temperature, it should be less than 0. and delta G dG at constant P and T should be less than 0. So these are the condition for spontaneities. So what is the wrong condition here is not a condition of spontaneity is option number A. This next question, if the fundamental equation of thermodynamics is given by U is equal to or in terms of U S V N, then which of the following is correct? So try to solve this problem. So we know the thermodynamic uh, property that is internal energy U is a state function, and being a state function, it is exact differential, and because of its exact differential, we can write it. It's its change we can write in the form of, so we can write its change in the form of U is equal to del U by del S at constant V and N in S plus del U by del V at constant S and N in V plus del U by del N constant S and V and N. So this quantity del U by del S at constant V and N, it should be the temperature, but it is not. Here, this is not, it's constant V and P is given. So this will not be our answer. The second one is P is equal to del V by del U by del V S and N. So this quantity can resemble to the internal pressure. Okay, not the pressure. It is the internal pressure. So P will not be equal to del U by del V. But third thing, del U by del N at constant S and V, it's a definition of chemical potential. And the last thing is S is equal to P and T constant del U by del V. This is also not the relation. So this should be correct because the second option, it seems to be correct, but it's an internal pressure And uh, the most appropriate answer is C, the definition of chemical potential. So third question is, which of the following is not an intensive property? Solubility, density, temperature, and volume. So we know the extensive and intensive properties. We have seen back in the first or second week this lectures. These intensive properties are the properties which uh, does not depend upon the quantity of the substance of given substance or the system, but extensive properties are depends upon the quantity of the inside the system. So the same thing, the solubility, we know we can define it per unit quantity. Density also we define it as a per unit mass, or it is the same. All doesn't depend upon the the number that the number or the size of the system. Density also will not depend upon that, and the temperature is also the intensive property, because it also whatever the temperature will be the constant for entirely, uh, whether you take small quantity of a given system or the larger quantity. Temperature will be the intensive property. Density will be intensive property. Solubility will be also intensive property. The intensive property which is not is the volume. Only quantity is not the intensive property, is the volume. Fourth question, del H by del S at constant pressure can be is equal to, take 2 3 minutes to solve this problem. So we know the differential relation, uh, del H is equal to, sorry, dH is equal to TdS plus VdP. We need to find out what is del H by del S at constant pressure. If you see here, this equation, we can differentiate with del S at constant pressure. So here T plus, as the pressure is constant, dP, the change in pressure will be zero. This term will turn out to be zero. So this will be T. So the final answer should be the T, option number A. So next question. Minus 1 by V del V by del P at constant T or we can say at constant temperature is Joule's coefficient, isothermal compressibility, specific heat capacity, or adiabatic compressibility. So in this problem, if you see the equation or the quantity is minus 1 by V del V by del P at constant temperature. So as the temperature is constant, it should be isothermal thing. So it's isothermal, and the del V by del P is nothing but the change in volume is related to compression or compressibility. So it should be the isothermal compress. Option number B. Next question. If alpha is the coefficient of a thermal expansion, then del T by del V at constant pressure is. So four options are given. Try to find out. So we know what is the coefficient of thermal expansion alpha. It's nothing but 1 upon P uh, del V by del T at constant pressure. So if we multiply both side by volume, is to find to be del V by del T, just constant, sorry, here constant pressure. And we know there is relation. We can use del V by del T at constant pressure. It's nothing but del T by del V inverse constant pressure. And if you use that, then you will get del T by del V at constant pressure is nothing but 1 upon alpha. So the option must be option number A. Next question is Helmholtz free energy represent the total heat content of a system, energy contained in the system, amount of useful work that can be obtained from a closed system at constant temperature and volume, none of the above. So the Helmholtz free energy represent the amount of useful work that can be obtained from a closed system at constant temperature and volume. So we know what is the Helmholtz free energy. A is equal to U minus Ts. So U is internal energy and Ts is nothing but the energy uh, which gone to entropy, change, increasing the entropy. So that energy we subtract from the total internal energy that would give you the amount of useful work that can be obtained from the closed system. Means the closed system is there will not be heat exchange. So at constant temperature and volume. And Ts is the energy that gone to in, increase or decrease in the increase in the entropy of the system. So that Ts is nothing but the energy that gone into uh, that part of the uh, system where the entropy get increased, and because of that, that energy is not useful for doing work. Once the energy used for increasing the entropy, that energy is no more useful to do the work. So using that principle, the only available energy is nothing but the Gibbs-Helmholtz energy for in case of closed system, which is available to do the useful work. Useful for work in the sense the expansion work, or we can say the expansion work is the same as that gas does on piston, or gas does the work in opposite to the pressure, some pressure of uh, atmospheric pressure or some other kind of forces. So that is called we call as a useful work. So A, that is the Helmholtz free energy, gives you the useful work that can be obtained from a closed system at constant temperature and work. So option must be option number C. Question number 8 is which of the following relation is not correct? So we have seen the four relations. We have to find out what is the incorrect relation. So here we can see option number D is uh, incorrect relation, because change in Gibbs free energy is nothing but minus S dt plus VD. Okay, the sign change is there. This is correct and this is wrong. So the option number is 4. So next question is del U by del V at constant entropy is nothing but, we need to find out. Try to work out this problem. Take through 2-3 minutes. So we know the thermodynamic relation du is equal to TdS minus PdV. We need to find out what is del U by del V, constant entropy. So we differentiate with respect to del V at constant entropy. So that will give you entropy is constant. So this term will be 0 and minus P del V by del V is nothing but this 1. So it's a minus P. So the answer should be, sorry for that. So answer should be minus P, option number 2. So the last question, question number 10. Find the incorrect Maxwell relation. Take your own time, 2-3 minutes to determine which is the incorrect Maxwell's relation. The same uh, mnemonics we have studied before, just in the beginning of this discussion. Use that and determine which relation is incorrect. So if we see here, del T by del V is del P by del S. If you take T and V are directly proportional, but P and S, if you increase the pressure, that entropy must decrease. So inversely proportional and the negative sign must be there. So this is the relation is right. Del T by del P is del V by del S. Similarly, if you verify the in similar way, V and S are directly proportional, T and P are directly proportional. So there will be this relation is uh, correct. And next relation del S by del V. Uh, Del S and del V is equal to del P by del T. So P and T are directly proportional. S and V also directly proportional. So this relation is valid. But the last relation, if you see del S by del P, del V and T are directly proportional, but S and P are inversely proportional. So there should be a negative sign, and this is a wrong relation. So this is the last question. So if you're having any doubts, you can ask. I'm here up to 9 p.m. Please ask if you are having any doubt regarding any question that we have covered in last 10 or this 11 discussion sessions. You can discuss this or the problems that are there if you are facing any. Thank you very much for giving the session. We will meet next week on Tuesday, uh, 7 to 9 p.m. I think that in the last session, at the 12th session, and we will be having a revision of entire course and some practice problems. Thank you very much for the session.